Hello everyone, welcome to this session. So, this is about we have been discussing the PLL building blocks, and in the PLL building blocks the last one which we are going to see is the clock frequency divider. Okay, clock frequency divider. So, this is quite simple by the way as compared to the other blocks. So, what we need is we need a block where we give in the input clock, let us call as clock in, and we get clock out, and clock out should have frequency which is lesser than the input frequency, and it should be something some number which is fed externally. Okay. So, to do that one of the easiest way of implementing a frequency divide by 2, let us first look at that. Frequency divide by 2, quite often you use that, divide by 2, divide by 4 and so on. So, it can be implemented by using a D flip flop. So, you have D Q Q bar, you have a clock, and the output of this D flip flop is connected in feedback in this manner. Okay. And this is your clock in and this is your clock out. Okay. So, and the D flip flop is surely connected to VDD and ground. Any circuit which we are using here has VDD and ground connection. So, if you look at it, when I give my clock in like this, you can start with the initial value Q as 0 and Q bar as 1. So, this is clock in. I am assuming that initial value of Q or clock out is 0. That means Q bar is 1. If Q bar is 1 and you get a rising edge on this D flip flop, right, the input which is Q bar, it is 1 right now, you get a rising edge on clock in. So, you get output 1 and it remains 1. The next output is going to change only at the next rising edge. So, when you get the next rising edge, till that time, because Q bar has now become 0, okay, at the next rising edge you get your input was 0. So, you get divided by 0. So, in this way you can very well implement divide by 2 clock. Okay. Now, if you want any frequency division where frequency division is in the order of exactly frequency divide by 2 power n, okay, whether n is 1, 2, 3, 4, it is like divide by 2, divide by 4, divide by 8, divide by 16 and so on. You can cascade these blocks. It is right. So, I will just erase this part a bit, remove this also and connect it the smaller clock, right, and I am going to cascade this. So, okay, so this connection has to go like this. This is clock in, and similarly you can keep on going to have divide by 2 or divide by 4 and so on. Okay. Now, these D flip flops which you are going to use for this particular division, these D flip flops which are commonly used, there are two kind of flip flops which we use. One is, you can say, a strong arm latch based flip flop, okay, and other is TSPC based flip flop. Okay. These are the two commonly used flip flops. TSPC based flip flop has a lesser power consumption in general as compared to strong arm latch based flip flop, and it is also quite fast, it can operate at a higher frequency. So, let us look at this TSPC based flip flop. Okay. So, what you have here is you have clock signals coming like this. Input is D, this is clock, CK here, and the output of this goes to another stage where the next two stages, these inverters are both N. You give clock here also and at this place, and the output goes there. I call this as B. The output of this stage goes to another stage NMOS, and this is here. Okay. So, this here and this is clock. The output here is inverted. So, if you want actually Q with respect to D, you can add another inverter and you can use that as D. This is Q. So, if you want to look at the operation, let us just look at it. You have clock and D. Let us say you are going to get the rising edge of the clock like this, right. And if consider the case when clock is 0. So, during the time when clock is 0, look at the signals B and A. Okay. So, when clock is 0, at that time if D is 1, that means your clock is 0 and D is 1. So, this transistor is turned off. D is 1 means B is 0. Okay. B is 0 and clock actually is 0, which is like this particular signal A is 1 irrespective of the input. At clock 0, A is 1, right. Now, A is 1, this transistor is cut off, whatever Q bar value you have, it will be there, and this transistor is also off. Now, if D was 1 and we see that your clock goes high, when clock goes high, at that time this PMOS transistor was initially active, but because this was off, so it was not doing anything. B still remains at 0, B remains at 0, clock goes high, this transistor turns on, A goes low. Okay, these two turn on, A goes low. If A goes low, your PMOS, this PMOS gets active. Okay, this NMOS gets active, but this NMOS is off because A is low. So, your Q bar signal actually goes high. Okay, high value because clock is 0. Q, we do not know what that Q value is. It depends on what the previous value you had, Q bar. Now, when you get the rising edge on the clock, what is going to happen is B was 0. So, at that particular point, because B was 0 and clock is high, your this transistor is still off, this transistor is on, but nothing will happen, A will still remain 1, A does not change. Okay. If A remains 1, clock goes high, your Q bar actually goes low. Okay. B still remains low because D is 1. Now, consider the case when D is 0. In case D is 0, at that time your B signal is going to be high here, and if B signal is high, A signal is surely it is also going to be high. Q bar, whatever state you have from the previous, it will continue, and then when clock goes high, because B was 1 earlier, that time your A signal will go low. If A signal goes low, then your Q bar signal will go high. So, what you are doing here is you are sampling the input at the rising edge of the clock, and here you are actually keeping this as a Q bar. Now, in order to have a D flip flop based clock divider divide by 2, you can very well connect it in this manner, right. This becomes a divide by 2 circuit with this feedback. You do not have any D here. Okay. If you want to cascade this, you can very well cascade this, right. This kind of frequency divider is used at the highest frequency, because you see that you are using like a minimum number of transistors to divide the clock by 2. The problem with this logic is, as the frequency of operation is reduced, these node voltages which are actually held at 1 or 0, right, they are not connected to VDD or ground all the time with a direct path. So, these nodes will start discharging, or you have subthreshold current which for a long off duration or long on duration in the for different transistors. Due to the subthreshold current, the leakage will be there, and then you will have a different value at these internal nodes. So, normally we do not use these TSPC based flip flops for frequencies like lesser than 100 megahertz, but this is very much technology dependent. Okay. For lower frequencies, it is not advisable. Now, and the reason is because the nodes discharge over a long on or off duration. The other flip flop which we talked about is the D flip flop, which is a strong arm latch based flip flop. So, strong arm latch based flip flop has it has a sense amplifier, as I will show you here. So, this is a strong arm latch. Okay. So, you have a cross coupled inverter connected in this manner. Okay. This connects here and this one connects here. You have an input pair and a clock. Okay. So, if I am going to give D here, there is an inverter here, I give here D bar. It is like a differential input. You have clock here and you have a reset thing at the output, which is also with the help of a clock only. Okay. This is connected to VDD. The output of this you can call as VO and VO bar. VO and VO bar, they actually go to an RS latch. So, you have a NAND based, this is the RS latch which we use. Okay, you can have a different method of implementation, but the operation should be similar. This is R and S, this is Q and Q bar. So, here R and S is VO and VO bar. Okay. Now, you look at it, the strong arms. So, let us call this one is normally called as sense amplifier. This complete is a strong arm latch. Okay. Sense amplifier, and this is RS latch. So, when your clock is low, right, clock is low, your VO and VO bar, both these nodes are held high. They are reset to VDD. Okay. When you have these things reset to VDD, your NAND gates are not responding to anything. Whatever values you have at Q and Q bar, that will be there. Now, when clock goes high, it depends on what was the value at D. If previously D was 1, a logic high, then you have D bar which is coming here as 0. So, when D is 1 and this node is 0, at that time what is going to happen is these two transistors get active. This is 1, so it will start conducting. This is off. When this conducts, your VO bar value will go down. Okay. Your VO bar, as your VO bar value goes down with the PMOS transistor, this value is held high. So, as Ck goes high, if your D is equal to 1, VO is equal to 1 or VDD and VO bar is 0. As soon as your VO bar is actually equal to 0, right, what happens here is your Q, this if VO bar goes to 0, your this output NAND gate output, this output goes to 1 and this output will go to, if this output goes to 1, then what will happen is you have 1 and 1, this output will go to 0. So, you can let us say this is Q and this is Q bar in our case, right. Similarly, if D was 0, at that time VO will be equal to 0, VO bar will be equal to 1 and if VO is equal to 0, in that case Q bar here will be 1 and Q is equal to 0. So, it is changing the output Q and Q bar only during the rising edge of the clock. It holds that value. After that time, no more changes will be taken into account because this cross coupled latch holds the value. It is a regenerative latch, it holds the value to 1 and 0 unless it is reset and brought to the same level and then again it will decide. Okay. So, these are the two flip flops which are commonly used. For highest frequency with lower power consumption, we would prefer TSPC. As the frequency goes lower, then we will prefer this. You do not have any problem here with any node for high or low frequency. In this particular case, you have direct connection to VDD or ground, okay, for the outputs. These are the two, but flip flops which we use. What we have seen so far is a divide by 2 or 2 power n. Quite often you need frequency division not only in 2 power n, you need frequency division like 4, 5, 6, 7 or something kind of that. Okay. So, those things can be realized by using divide by 2 or 3, divide by 2 or 3 is a basic circuit, and based on this basic circuit you can cascade such circuits to realize different dividing frequency division value. So, let us look at this basic divide by 2 by 3. There is a lot of literature which you can read how to cascade this divide by 2 by 3 circuits and how the frequency will change. Okay. So, we will look at basic divide by 2 by 3 circuit. So, here you use latches like this, you will have D, Q and a clock gating circuit. Okay. So, let me just make this as a clock here, right, this, this and this. So, there are 4 such latches. Similarly, you have another latch D, Q and clock, and this will come at the output like this. Okay. Oh, there is nothing Q bar here, and okay. Okay. 2 of these latches are actually clocked at rising edge of the clock and the other 2 latches are clocked at falling edge of the clock. So, these 2 are at the falling edge of the clock and the other 2 are at rising edge. So, I will just give the clock input here. Okay. Then the output of the one which is clocked at the rising edge, I call that as LP1 and LP2, okay, and the one which is at the falling edge, I call that as LN1 and LN2. The outputs of this is input frequency. The output of these latches are QP1 and QN1. This one is QN2 and this one will be QP2. Okay. the output of this connects here, and then you have a NAND gate which connects it like this, and you have this particular one coming from this side. To control the divide by 2 or 3, we use a NAND gate. We will see how the division happens by 2 by 3, by the way, just hold for a minute. So, you have one connection coming from here and another connection is external connection P. Okay. This QP2 is also quite often written as M out. We will see what it does. Okay. So, now with this, in the presence of these latches, this is like a state machine which you will see. I can write my QP1, the next state of QP1 is equal to whatever value you have at Qn1 and Qn2. So, this is Qn1 bar and Qn2 bar because of this NAND gate effectively. Then Qn1 plus the next state of Qn1 is nothing but previous state of Qp1. The next state of Qp2 is your previous state of Qn1, and the next state of Qn2 is equal to your previous state of Qp2 times P. If P is 1, then it will have, otherwise it is going to be 0. Okay. Now, in this case, you will have, if P is equal to 0, then the output frequency you can take at any node. These are all having the same frequency at the output. So, if you want, you can take this as F out, or even M out signal or QP2 signal is also going to have the same frequency. Then you here, if P is equal to 0, you divide by 2, if P is equal to 1, you divide by 3. Okay. How it is going to do? Let us look at the state machine for this. So, to begin with, let us choose these states. Let me define the state first. So, state is Qn1, Qn2, Qp1 and Qp2. These are the states. Okay. So, we start with the state, let us say Qn1 is 0, which is here, and Qn2 is also 0. So, 0, 0, if Qn1, this is just like initial state, you can also fix that in the beginning. Qn1 is 0, Qn2 is 0, which is going to say that Qp1 can be 1 and Qp2 is going to be 0. So, this is the initial state. From here, you are going to look at when you get the falling edge on the clock. Okay. So, when you get the falling edge on the clock, I am going to denote that with as phi bar. Phi is the clock. You get falling edge on the clock. So, based on the previous state, at the falling edge on the clock, only your Qn1 and Qn2 will change, Qp1 and Qp2 remain same. So, this remains same, you have 1 0. Qn1 is Qn1 plus is Qp1, which is 1, and Qn2 is P is always 0. So, this will remain at 0 at phi bar. Then in the next time when you get at the falling edge, this happens, then at the rising edge, which is phi, your Qn1 will remain, Qn1 Qn2 remains same, it is the time for Qp1. So, what you see is Qp1 plus is Qn1 bar times Qn2 bar, Qn1 and Qn2, this is 1 or 0. So, it will remain 0, this will become 0, and Qp2 is Qn1, so which is 1. Then you get another falling edge in the clock cycle, right. So, when you have falling edge, your Qp1 and Qp2 remain same. For Qn1, Qn1 plus is Qp1, Qp1 is actually 0. So, this is 0, right, and Qn2 it remains 0. Then you get a rising edge on the clock, and rising edge on the clock, you know that your this state will be retained, and what happens to QP1 plus is you have 0 0. So, this becomes 1, and then you have QP2 which is QN1 which is also 0. So, this cycle actually repeats here, right. If you look at this cycle, what you are going to see here is this is happening at the falling edge and rising edge. With every falling and rising edge, you count half a clock period. So, 1, 2, 3, 4. After 4 half clock periods, the state repeats here. Okay. So, what it means is that if you have a clock like this, you can start from any state here. If you have a clock here, so on the first falling edge 1, then rising edge 2, then falling edge 3, then rising edge 4. So, after this the state repeats. So, if it is 0 0 1 0 here, it is going to come 0 0 1 0 here state in the fifth. So, this is how you are. So, after every 2 clock period, output is repeating. Now, the other thing which you can see here is whether you take QP2. So, QP2 here it is 0 0, then it becomes 1 and 1, which means in this if I look at the digital signal at QP is 2, QP2 is 0 for 2 of this consecutive and then it is 1. So, this particular signal is half the frequency of your F in. Okay. And if you want to get this divide by you want to have you can invert it at Qn1 and you can take this as F out if you are just doing divide by 2. Now, what happens in divide by 3? It is better that I do it here itself, because the state is diagram is here. Okay. So, I am going to start with the state, let us say start with the same state 0 0 and 0 1, 0 0 and 1 0. You get a falling edge on the clock. When you get falling edge on the clock, your Qn2 and Qn1 only change. So, I will QP1 and QP2 will not change. Okay. So, Qn1 this remains 1 0, Qn1 plus is QP1 which is 1 and Qn2 plus is QP2 times P. Here P is 1 for divide by 3. Okay. So, P is 1. So, this is 0. You go to 1 0 1 0. Then you get a rising edge, right. Rising edge here you will get the same state, because P only affects the falling edge, it does not affect the rising edge. So, I will get 1 0 0 1 same here, then you get falling edge. So, falling edge QP1 remains same, QP1 QP2 remains same, Qn1 and Qn2. So, now you see Qn1 is QP1 which is 0 and Qn2 plus is QP2 times P. QP2 is 1 here, P is 1. So, this becomes 0 1 0 1. So, your fourth state is different from here. Then you get another rising edge of the clock. So, rising edge of the clock Qn1 state remains same, QP1 is your Qn1. So, this is also going to be 0 and QN2 sorry QP2 is Qn1 which is 0, right. Then you get falling edge on the clock. When you get falling edge on the clock, what you see here is this remains 0 0, Qn2 is QP2. So, you get 0 0. Then you get rising edge of the clock, this remains 0 0 and your QP2 is QP2 is QN1 and QP1 is QN1 bar, QN2 bar. If QN1 bar and QN2 bar is 1 0. Okay. So, if you look at it, we count how many half clock cycles 1, 2, 3, 4, 5, 6. So, after 6 half clock cycles these signals actually repeat. So, when they repeat, you know that if it is repeating after 6 half clock cycle, then it is like repeating after 3 actual clock cycles. Every phi and phi bar is your clock half clock period here. Okay. So, if I have my clock cycle like this, okay, let us start to look at here QP2, which is M out. So, QP2 is 1, the falling edge, I should start with the wall. So, QP2 is 1, it remains 1, then it becomes 0, okay, then it remains 0, it is 0 here and it is 0 here. Okay. So, 1, 2, 3, for 4 of 1, 2, 3, 4, for 4 of this it remains 0, then it again goes 1. Okay. So, this is the period of the divided clock. Okay. Previously, this is the period of the divided clock. So, what you see here is that the divided clock is you can do a division by 2 or division by 3, and the divided clock can be any of these signals for the division by 2 and division by 3 circuits, right. Then the important thing here is that you do not have a 50% duty cycle. Okay. This is only your T input. So, the duty cycle of the divided clock here for divide by 3 is not 50%. Quite often it is okay not to have it at 50%, it will work fine if things only depend on the rising edge of the clock. Okay. So, now if we want to have any division ratio, what you can do is you can cascade these divide by 2 by 3 circuits. Okay. There is a NAND gate which is going to, this is M in. Now, you will divide by 3 only when Mn is 1 and P is also 1. You will not divide by 3 otherwise. Okay. This is needed when you cascade these blocks. So, I will just, this block is equivalent so, well, you have this also, this is F out here, you have F in, F out, this is divided by 2 or 3, you have M out and M in, these are also the inputs. Okay. So, you cascade this block. So, I am going to cascade these two blocks, this is just an example, and the output from here it goes to this, and this is something you get with the NOR gate. Okay. Your M out from first it goes here, this I call this as M1 dash, this Mn is connected, always connected to VDD. Okay. So, that means whatever you want divided by 2 by 3 in this circuit, it is you can get it, this is F1, F2, you can get finally divided clock at the same flip flop at where you are feeding the inputs. Okay. And then what you have here is this P0, okay, you have P also. So, I will just write this as P. So, this is P0 and then you have here P1 and this particular signal is going to add as P2. So, based on this P1, P2 and P3, you can load this using some registers. Okay. So, based on this P1, P2 and P0, P1 and P2, you can get different values of the division like 4, 5, 6, 7 in this case. Okay. This is an example, you can work it out that how this is going to give you divide by 4, 5, 6 and 7. Okay. So, when you want a larger division ratio and such kind of numbers, you can actually cascade such blocks, load these control voltage, control signals P0, P1 and so on, and you can get the division ratio which you like. Okay. So, that brings us to an end of the discussion on the building blocks of PLL, and next we are going to see what are the other problems with the PLL or what we can do to improve one or the other performance metric of the PLL as a whole. Okay. Thank you.